Today we're looking at some sample problems from section 10-3, and we're dealing with regression. Now these problems use the same data that was used in section 10-2. So I'm going to begin with 24 simply because I have the data for 24 in the calculator right now. And so 24 in section 10-3 is found on page 530. And then I'm going to work backwards up the example list. All right, 24 says find the best predicted temperature at a time when cricket chirps 3,000 times in 1 minute, and what is wrong with this predicted value. So we have chirps in 1 minute are our x's, and temperature in degrees Fahrenheit are our y's. And we entered those values into the calculator. My calculator here to show up. Okay, so we have 882 is matched with 69.7, 1188 with 93.3, and so forth. So the number of chirps per minute and the temperature in degrees Fahrenheit, L1 and L2. So now what we want to do, we know that from the previous time, and let me just go ahead to, and we're going to calc, so I need that. And I want regression, linear regression. And notice the calculator uses ax plus b. So in the case of the calculator, the slope is a and the y-intercept is b. So instead of an m like we used in algebra, it's using an a. And also, again, different from what our textbook uses. So I want L1, comma, L2. And you'll notice that I'm using exactly the same key path that I used last time. So actually the data was given to us last time, we just didn't realize it. So you'll see the A, that's going to be our slope, and B is 27.628, etc. Alright, so let me jot these down so I won't have to go back and forth. So what we know our equation will be is y equals 0.05227. I'm going to go ahead and take 6 significant digits. 2, 4, 5, 6. Okay, 2, 2 will make it. Alright, so times x plus 27.6284 would give us 6 significant digits. Okay, now our problem wants us to make a prediction, and what we said was our R was strong enough. I think we compared it to 0.707, that we do have significant linear correlation, and so they want us to make a prediction for a cricket that chirps 3,000 chirps in 1 minute. So let's do that with our calculator. And because of the fact I'm making a calculation, I am going to use 6 significant digits, 22722 times our 3,000, that's our value for x. Okay, and then it's plus, it is a positive, plus 27.6284. Alright, so our predicted temperature is 184.4 degrees Fahrenheit. Okay, or about 184 degrees. Let's see, they don't tell us. They don't tell us what kind of accuracy to use here. So okay, so that's for 3,000 chirps per minute. Now there is a problem with this particular value that was chosen, the cricket chirps being 3,000 times a minute. And what you want to do is you want to look, let me go back to the calculator, go back to edit. Look at the values that we have for L1. Do you see anything that's anywhere close to 3,000? No, it turns out that the largest value we have is 1188. 1200, I guess, would be the largest one, 1200. So 3,000 is more than double that, almost triple that. So we've gone way outside the original range of X values. Anytime you do that, the regression equation does not make a good prediction. And my question would be, is it possible for a cricket to chirp 3,000 times in a minute? Certainly we would hope that outdoors the temperature would not be 184 degrees Fahrenheit. So the value of the 3,000 chirps in 1 minute is well beyond the scope of the available sample data. So extrapolation might be off by a considerable amount if a cricket could indeed chirp at 3,000 times in a minute. So there is a problem with that, even though we were able to make a prediction and come up with our equation. And I should write that there, y equals 0.05 to 3x plus 27.6. That would be the leading zero is not significant, so we have 3 significant digits here and here. And usually they, in our book, they put a little hat over top the y. Sometimes I do and sometimes I don't. So that would be our regression equation. We would plug the 3,000 in here to come up with this temperature of 184 degrees, which seems very unlikely. Okay, let's move back up the page to number 22, and this is a table of car repair costs. It says find the best predicted repair costs for a full rear crash for a Volkswagen Passat, given that its repair cost from a full front crash is $4,594. How does the result compare to the $982 actual repair costs from a full rear crash? So we've got a table of front crashes and rear crashes, dollar amounts for the repair, and X is the front and Y is the rear. So we need to go to the calculator, and let me clear my lists. Okay, so we want to, let's see, 936, 987, 978, 2252, 1032, 3911, 4312, and 3469. Whoa, I went way over. There we go. Okay, and I want 1480. Then 1202, then 802, 3191, 1122, 739, And last of all, 2767. Okay, so we want to go to Calc, and we want to do the regression L1, comma, L2. Okay, so our R this time is 0.282, and we have 367. So we need to go to our table. For 7, we need 0.754. So the absolute value of R, the negative 0.283, the absolute value of that is less than our table value of 0.754. So we do not have significant linear correlation. All right, no significant linear correlation. So how do we make a prediction when we do not have significant linear correlation? Well, we know from the previous problem, when we do, we use the regression equation and we plug the number given to us for our x into that equation and then solve it. When we do not have significant linear correlation, we want to find the average of the y value. So I'm going to go back to the calculator, and remembering that, and I'll go to edit here, my y values are in L2. So I'm going to go to Stat, Calc. I want one variable, statistics. I need to specify though that I want L2 because that's where the y is. Okay, and it's calling it an x bar. It just calls everything x bar. But that's going to be our y bar, 161471. Okay, so now the actual repair costs were only 982. So how does our result compare to the it's quite different. It's very different. This is the actual. And so the answer to the question is very different from what the actual cost was. A difference of about almost $7,000. So we're talking about quite a $700, not $7,000, $700. So it is a very different value.